You know, I'll bet if you ask the average person what a statistician does, he'll eventually reply, well, he's a number librarian. And he's got a point, because that's where statistics really did start, in the techniques for collecting large masses of data and then cataloging these data, and then perhaps the most important thing of all, finding the bit of data you wanted when you needed it and so forth. But gentlemen, that's not the kind of statistics that we are going to be talking about. We're going to be talking about the applications of statistics in a scientific environment. Here, this is usually the situation where the data are not, large in number. We don't have large masses of observations. We only have very few observations indeed. And we're anxious to talk about applications of statistics which are reasonable and valid in a research environment, or in a pilot plant or semi-works plant, or even on the production floor. Now, consider a research environment. What is the objective here? The individuals involved with the research are anxious to develop mathematical models which will describe various physical phenomena. And of course, they're very anxious that their mathematical models will apply not only in their own laboratories, but in laboratories throughout the world. And it's essential, of course, to take the data very, very carefully, to very carefully control the environment. And of course, it's not at all uncommon that the amount of data is very few indeed, the amount of numbers recorded. But then there's a pilot plant situation. Here the problems are a little different. The individuals involved are experimenting with the pilot plant in an effort to determine what are the optimum operating conditions. What are the various speeds for the pumps? What are the alternative flow rates and so forth which are possible? Perhaps we should try different temperatures in our claves. And what other variables can we in fact vary so that we get the maximum possible yield out of the process? And then you can think of data-taking situations and experimental designs in a production environment. Or here's a situation where the data are very expensive indeed to come by. But if we do a successful experimentation in a production environment, of course the rewards are very great, because modest increases in the efficiency of production of a plant will generally mean vast rewards indeed to the company. Now, what is the outstanding characteristic of the data we get in an industrial environment? It's expensive, usually very expensive indeed. It's not at all uncommon, as you all well know, to see collections of observations in which each observation has cost several $100s. It's not at all uncommon to see experimental programs that have taken 20 or 30 observations and so on which we finally sit down and try to unfold what Mother Nature is really doing, and not being terribly successful with it at all. Now, we're interested in statistics because it's supposed to help us unfold what's really going on in the plant, or in the laboratory, or in the pilot plant. And this is intimately involved with the scientific method. So what do you say we have a quick look, speaking in broad terms, of what the scientific method is all about? The scientific method invariably begins with some question that's raised and searching for an answer. For example, suppose you were a chemist and you were asked to produce a certain chemical, let's say chemical gamma. You'd think about it a while, then you'd say, I think if I mixed alpha and beta together in certain concentrations, I ought to get some gamma. And so actually you start out with an idea or a conjecture. And then you begin to design the experiment. You say, well, what concentrations of alpha and beta shall I use? And I wonder what temperature environment I should put in, and shall I stir it or not? And what kind of a clave shall I use? And so forth. You'd actually think in terms of designing an experiment, trying to anticipate the environments that you want to organize for the collection of the meaningful data. And then, of course, you have to run the blooming experiment. And that's a large problem in itself, actually conducting the experiment. And after the experiment is completed, you take the results of the experiment and submit it to analysis. Now, what's the purpose of the analysis of the data coming out of the experiment? You can see this chemist. He's produced some gamma, to be sure, as a result of his initial experimental design, but upon seeing the amount of gamma and upon experiencing the experimental environment, he has new ideas about how he might improve his performance and so on. And so the analysis invariably leads to new conjectures, and we start around again, designing another series of experiments, running the experiments, and so on. And in this fashion, we acquire that amount of knowledge which is necessary to answer the question that's raised. Of course, the amount of knowledge is different in a research laboratory than it is in a pilot plant, than it is on a production floor. But this is the general technique which is evoked. And of course, the experimenter, the engineer, is predominant because he has the ideas. He chooses the variables that enter the experimental design. It's his ability to do titrations and perhaps do a little midnight requisitioning to get equipment or to badger money out of his boss to run the experiments and so forth. He enters here, and of course, in the analysis of the data. And one strange thing you want to be aware of here is that different experimenters analyzing the same data are going to come up with different ideas. But here is, roughly speaking, the scientific method. And where does statistical techniques come in? In two places. The purpose of statistics is to unfold the information in the data, to help in the analysis of the results of the experiment. And the purpose of the analysis, of course, is to lead to new ideas and new conjectures. And so our use of statistics is to stimulate this particular mental jump, which is vital to the scientific method. And of course, our ability to resourcefully analyze the data depends in large part on how the blooming experimental design was put together in the first place. And there are various methods of organizing the way in which the experiment is designed, which will greatly contribute to our ability to do a resourceful analysis of the data. Very good. But all of this suffers from one grave handicap, and that concerns the occasion when we repeat the experiment. When you repeat an experiment, what happens? And the answer comes back, you won't see the same thing twice. You cannot repeat an experiment and observe, get the same response on two different occasions. Let me explain that a minute. Let me show you a quick illustration. Let me repeat a performance. I'm going to write my name twice. Now, by golly, you know, I'm very, very familiar with that scribble. And I've repeated it here under operating conditions which are about as homogeneous as you could possibly make them. And yet you know and I know I cannot reproduce the performance. There is an intrinsic variability which is implicit in every operation which we as human beings perform. What happens, of course, is that when we may take an observation in practice, what we get is not the measure of the true response that we're trying to follow. We measure the true response disturbed by an error. Now be careful of that word error. I don't mean by that a mistake. I don't mean that there's been a transposition of the digits of the numbers, or if someone's misplaced a decimal point or something of that kind, a sort of a mistake. What I mean is the kind of error which impinges on the data-taking procedure. And the magnitude of that error and the sign of that error cannot be predicted in advance, but it's always with us. There's a source of variability which impinges on every data-taking process, and the consequence of that error is that the observations we get upon repeating an experiment will differ. Well, all engineers know that. You know, suppose you were an engineer and you were breaking nylon filaments, and every time you broke the filament, you observed the response 17 units. You know, break a filament, 17. Break another one, 17. Break another, 17, and on into the night. Now, what would happen if you got data like that? Well, you know, everyone would say, well, gee whiz, the meter's stuck or something is wrong. You anticipate, you sort of expect variability in your observations. And, you know, this sometimes gives rise to the reason why many engineers are not willing to repeat experiments. They're sort of unconsciously or consciously afraid of how variable the results would be if they did indeed repeat the experiment. Well, now, what we're going to do in the first 6 or 7 lectures of the ensuing series of lectures is try to get you acquainted with the problems of estimating the variability in the data. how we can construct statistics out of the observations that we have that are most meaningful in demonstrating what is really going on. We're going to talk about tests of significance and how to make interval estimates. These are beginning lectures, if you will, on statistics. And they're a little difficult, perhaps. A student once told me that learning statistics was, analogous to someone who's trying to learn bridge from a person who could only speak Iroquois. And, that's what you're up against. I speak statistics, and I'm trying to teach you statistics. And you sort of have to learn the language and the manipulations at the same time. And it can be painful on occasion, but not too painful. Really, the material is very, very simple indeed. Now, when we get through with our sort of background material on statistics, we'll be able to contemplate some of the problems of simple experimental design. Now, this shouldn't come hard to any of us. You don't have to be an engineer or a scientist to worry about experimental design. All you can do is sit home of a night in your living room and watch the TV commercials in which, we say, which detergent cleans the laundry best? Or, is this towel whiter than that towel? Or, if you like, will a change in spark plugs improve the mileage performance of your automobile? Well, I'll tell you. Here we see excerpts from just such a commercial. Here's a commercial in which their individual cars have all been loaded with the same amount of gasoline, and here they are on the test track. And the trick is to see how far they will go. Then all these automobiles are equipped with one kind of a spark plug. We see them coming across the desert and all gradually stopping. And then the distance that they've run is very carefully measured. They're re-equipped with a new supply of gasoline, and all the spark plugs are changed, and we start over again. And of course, in this instance, we find out that by the changing to the newer spark plugs, we do indeed increase the mileage performance of the automobiles. Now, in this particular instance, the answer is, in a sense, obvious. In spite of all that variability which we observed between those automobiles as they went down the test track and so forth, in spite of all that variability, it is very clear that there's a real difference demonstrated between the new spark plugs and the old spark plugs. But what happens more often when you take data of this kind? The variability is present, but of course the difference, the real difference between the two alternative spark plugs, or the two alternative treatments, or the two alternative suggestions and so forth, is small. We run up against the difficulty of trying to find out which is best in the presence of all this extreme variability. And that's where some of the arts of experimental design come in. Think back to that experiment. Look at all those cars. Those cars are different. And then what about the drivers in the cars? They're different as well. These are sort of obvious sources of variability which are contaminating and helping to confuse our analysis of what we really want to study, which spark plug is best. And so we're going to talk initially about a class of experimental designs called the blocked designs. We're going to talk about randomized block designs and balanced incomplete block designs, and then designs with such esoteric names as Greco-Latin square and so on. These experimental designs are methods by which we organize the collection of the data so that we can eliminate or block out the large and sort of overt and obvious sources of variability. So when it comes to making the comparison between the two types, or between k different types of spark plugs, we can make these comparisons purged of these sources of variability. This has the result, of course, of permitting us to get along with fewer data, which translated means less money for the same amount of information.